Alright, so the point of this tutorial is to look at position time graphs for various objects. We're going to focus on one specific case that's similar to the lab that you did with your monster truck. I'm going to base this lesson on two hypothetical vehicles, a VW and a truck, but they're similar to what you have from your graph in the lab, and then we want to be able to really extrapolate this to all objects that fit a similar type of motion. Okay, so again, our focus is going to be position versus time. So when I look at those two graphs, I see that there's something very different about them. The VW is starting here at the origin. It's a fairly steep line, and then the truck starts somewhere up here, and its steepness is not as great. So we can ask a few simple questions about it. First thing we can ask is, what is increasing? It's a very simple question, but sometimes we jump ahead of ourselves and answer something that is not there. What's going up is from here to the end, or from the truck's beginning to the end, is simply the position. Okay? Now, what's the big deal about saying that the position is increasing? It's basically another way of saying we're moving, and we're moving forward. Okay? We're moving away from our starting point. All right? But that's an important thing to establish. So we can see motion on a position time graph by the fact that our position is changing. Yet, there are a lot of ways we could show forward motion. We have particularly in both cases a straight line. They could be curved, they could be combinations thereof. So the straight line is telling us something else. So what do we know from math is constant about any straight line? Well, that's the slope. So the fact that both vehicles have different slopes tells us something about their motion. And so we can ask ourselves, what does the slope represent? Well, we can kind of get an idea of what that is by calculating the slope. If I were to choose 2 points on the line, what I'm choosing, when I do slope from a math standpoint, it's change in y over change in x. But in this case, our change in y is change in position, which ironically is the change in x, because we're calling position x. And our change in x is the change in time of the graph, okay? And so when we go to find a slope, we combine them, we see that slope, in equation-wise, is this. And how do we interpret that? Well, anytime we have time in the denominator, that represents a rate, okay? So we're looking at the rate at which something is changing. What's changing? Well, that's simple. That's the position. That's what's in our numerator. So anytime you find a slope of a position time graph, you are really finding the rate of change of position, which is a quantity in and of itself, a very, very important one that we're all familiar with, but this is where it originates. So the rate of change of position, you're going to figure it out, is by definition velocity. And if we're not interested in direction, or if our direction is 1, we're moving in forward or all backward, then we can say that's also speed. Okay, so that's probably the most important interpretation we can get from this type of graph. The most important lesson from this tutorial is that velocity or speed is the slope of a position time graph. Now there's a little bit more subtlety to that when we get into more complex motion, but that's the essence. So in this particular situation, if we want to calculate the slopes of each vehicle for the VW, okay, that's pretty straightforward. We're starting at 0 position, we're ending at 120 position, and it's taking us 3 seconds. So I'm not going to write out all the work here, but that's essentially 120 divided by 3 centimeters a second. So that's 40 centimeters per second. Okay? And you kind of know that. So with that steepness of slope is telling us for every second that goes by, the vehicle is going 40 centimeters further. And it's a constant rate. So in other words, we're always going 40 centimeters per second. For the truck, we just got to be a little bit more careful. Our beginning point is 60, our end point is 120, and it's taking 6 seconds. So 120 minus 60 is 60 divided by 6. And so our rate of change of position is 10 centimeters per second, or our speed is 10 meters per second. So we can see intuitively that the steepness of the VW is greater than that of truck, and we can see from our calculations it's 4 times as steep. We're going 4 times as fast. All right, how about the y-intercept? Does that mean anything? Of course it does. And it doesn't take much to realize that the y-intercept represents the initial position. Okay, and that's going to become important when we develop equations later. So obviously the VW starts at position 0, and the truck starts at position 60. And if we were having a race, in other words, they both start at the same time, which this graph implies, eventually the VW is going to catch up to it right about there. Okay, and then afterwards, the VW is going to be, for any given time interval, if I choose some time right here, if I look at, well, actually, if I look at right here, the VW is always going to be past the truck. My resolution here is not good enough, you can see that, but you get the idea. All right, so some simple questions. At time 2, which vehicle is moving faster? Actually, let me change that to time, well, let's call time 1. Okay, it's not clear where that is on our graph, but let's say time 1 is right here. So if I trace it up, which one's moving faster? You've got to be careful. It actually has nothing to do at what time, because we know that the speeds are constant, so the VW is always moving faster. Which one is ahead? Now we can see that on the graph. At time 1, the truck is about 70 or so, and the VW is well behind that, so that's the truck. Okay, at any time are the speeds the same? You might be tempted to look at where they intersect right there. Okay, so the speeds are they the same? No. We already know that the speeds are different because the slopes are always different. Are the positions ever the same? Yes, right around 2.5 seconds, approximately. Okay, another way we can look at constant motion or constant speed is a one-dimensional model. And an easy way to think about that is, suppose each vehicle dripped paint from it at equal time intervals. How would the spacing of the drips look like? All right, so basically, if we start here with one drip, after a certain amount of time, we're going to have a second drip. And if we're going at a constant rate of change of position, then it's not hard to realize that the drips are going to be equally spaced. Okay, now that's pretty obvious. Now this is for one vehicle. If I draw it for the other vehicle, such as like this, and they're supposed to still be evenly spaced, I could ask which one's the VW, which one's the truck. Okay, and we can see that this covers more ground. The second one covers more ground in an equal amount of time, right? Covers more ground here. That's delta x for delta t. That must be the VW. Therefore, this one's the truck. And if I do it more precisely, the truck one would be 1/4 the spacing of the VW. We'll come back to that later on when we're looking at changes in speed. Okay, now what if we want to take the same information, right? You can't see it on the smartboard right here, so let me try to do a simple replication of the graph. So here's our truck, and then we have our VW. Okay, this is 3 seconds, this is 6 seconds. What if I want to look at the speed versus time? I want to translate this into a different type of graph. So to go from position time to a speed versus time, how would I go about doing that? Well, I would just literally take my interpretation and try to apply it to the graph. So let's take this VW. What do we know about it? It's moving forward. Okay, that's important because forward is a direction. We're going to call that, if we didn't state that outright, but the direction is positive here because we have a positive slope, and it is moving at a certain rate. We already determined that to be 40 centimeters per second. So that vehicle is moving at a forward at a constant speed, right? Forward, constant. You're going to be asked to describe these type of motions, and this is what you have to do. You just can't say moving constant because that's not clear enough. So I go over here. This is showing me velocity as a function time. Forward would be positive velocity. So we're going to always stay in this quadrant. And then constant speed means that speed is not changing. So if I choose a value here, I'll choose this hash mark here. I'll label that 40. I want to stay constant. And so I'd go constant, constant, constant. And it only lasted for 3 seconds. So I'd stop there. The truck, on the other hand, is also moving forward at a constant speed, but its speed is much less. It's only 10 centimeters per second. So what I would do is I would start, let's say, right here at 10, and it took 6 seconds to complete its trip, and so it would look like that. Okay? So notice that a position time graph and a velocity time graph, even though they're saying the same thing, look very, very different. So when you have a upward sloping position time graph, you get a flat velocity time graph, and if the velocities are positive, you're going to be above the you're going to be in the positive part of the y-axis. Now, we can do something interesting with this velocity time graph. How could we find the displacement at any given time? So nowhere on here do we see displacement. All I see is velocity and we see time. Okay, so how do we go about figuring out displacement? Well, we can kind of think of this as the reverse of what we saw with the position time graph. All right, so with the position time graph, we saw that the slope gives us velocity. So in a velocity time graph, we want to do the reverse of slope. So the reverse of slope is not slope, it's actually area. Okay, and this is an odd concept at first, but when you do it enough, it'll start to make sense. And for those of you doing pre-calc or honest pre-calc or eventually calculus, this is really talking about an integral. So if I look at the velocity time graph for the VW, I see that under the graph, under that curve, is an area that looks like a rectangle. Okay, and if I look at it for the truck, it's a really long, narrow triangle. And so the area of these shapes, they're both rectangles, is base times height. So if I want to do area of the VW, that's a base times a height. My base is 3 seconds. My height is 40 centimeters per second. So if I multiply them, sure enough, I get 120 centimeters. The units cancel the 120 centimeters, and so that's exactly what we saw before. If I look at the truck after 6 seconds, again, my base is longer, it took more time to get somewhere. It was only going 10 centimeters per second. So 6 times 10 is 60, and that's not right. I must have done my slope wrong. You guys catch that? Let's see, where are we? $120.60. I'm not sure what the. Okay, forget that last statement. This is supposed to be 60. Now, why isn't it the same as this? I forgot the fact that this is the change in position. So I got to be careful here. The area under the graph gives us the change in position. It was 60 during that 6-second interval, but we were starting at it. So our final position is equal to the change plus where we started. And since we started at 60 and we changed 60, that would give us being at the position of 120 after the 6 seconds. Okay, so apologize for that goof there. But again, when you find the area under the graph, okay, you're generally finding the change in position. And if you start at 0, that's equal to your displacement. If you start at something other than 0, then you add that to your change and you have your final displacement. So we'll do more with that in other graphs. All right, last thing I want to do with this before we end it is, what would the graphs look like if the vehicle turned around and went back to the original positions at the same speed before? Okay, so at time 0, let's take the VW. Where is it? It's at 120 units away. It's going to turn around, go back the same as before, so it's going to take 3 seconds to get back to its original position. And we know it's moving at a constant speed, so constant speed means a straight line, so the VW is going to look like this. Okay, so in other words, if we were to calculate the slope of this, we'd still get the magnitude of 40, but since this is a slope, it's going to be negative 40 centimeters per second. So in other words, we get a negative velocity. In other words, we've turned around. For the truck, again, we're starting at position 120. It's going to take us 6 seconds to do its motion, but it's not going to go back to 0. Whoops, so I got to go up to here, go over to here, so it's going to end up right there. So its graph is going to look like that. Okay, so the same slope, but it's negative. So a simple little point here is that negative slopes mean you're going in the opposite direction. Okay, in terms of velocity, we would have a negative velocity. So we wouldn't be up here in a positive, we would be down here. So we would start, one would be negative 20 or negative 10 for the truck, and then the car would be down here, negative 40, and that would go for 3 seconds back to the starting point. And we know we'd be at the starting point by looking at the area. If we look at the area under this one, we would find that it was negative 120, which means we're gone back to the original place. We went 120 at the beginning, now we're back to 120. Okay, that concludes this first interpretation of position time graphs.